and welcome to Project 152, your weekly specialist exam prep. Now every week we go through questions from the QCAA. If you stick with us the whole time, you'll have done every single one of the 152 questions they've released. This is week 24. Now I'm feeling a little bit sleepy today, but sometimes you just got to power through it, and we've got to power through it today. We've got 7 questions to get through. Let's go. So here we have a slope field question. Let's get into it. It says the slope field is this, but that information is not particularly useful to us. The solution to the curve this passes through point 3, -5. There it is. And the question is, what other point does it pass through? Now, with questions like this, you need to be willing to get rid of the super accurate mathematics that you do the rest of the time, and instead be happy kind of on a vibes-based kind of maths. Now, by that I mean, let's start at 3, -5 and trace our way through this slope field. You can see at that point, the slope of whatever graph is passing through there is straight up, right? So it's moving straight up, moving straight up. The slope is straight up, straight up, straight up. But look here, as we get here, the slope starts sloping just a little bit to this side, right? Boop, 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 boop. And so it's just going to pass to the left of Q. It can't pass through Q, because to pass through Q, it would have to slope this way and hit Q, but it's not. Okay, boop, 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 boop. And then, but we're still dealing with positive gradients here. And then we've got a negative gradient. And then it's coming down again. Look. Yes, there's a negative gradient. So you're thinking maybe it could go all the way down to here. But look at what was happening at that point. Like, forget the graph we've just been tracing. At that point, the gradient's positive. But to get from where we currently are to down to here, we'd have to be going negative. So that's not going to work. This graph looks something like bam, 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 to the left, turning a little bit, coming back down. You can feel this gradient negative, but then it starts sloping back up again, and then it's going to hit this. And the answer is P. It's not going to get anywhere near R because you can see it's sloping back again. Vibes-based mathematics. Our answer is P. Let's celebrate it. We'll go on to the next one. So here we have another question, and they're taking a bunch of samples of different sizes. And this was sample 1's confidence interval, and this was sample 2's confidence interval, 3 and 4. And the question is, which sample used the largest sample size? So, you're a statistician and you're collecting data about a population. If you want to get a pretty accurate measurement, you increase your sample size. If you increase your sample size, you're going to shrink your confidence interval. And the smallest confidence interval here is sample 1. So my answer is A. Now, why did that just pop up? Because I've spoken about that and I've said, hey, to decrease your sample size, to decrease your confidence interval, increase your sample size. But you can also, if you forget that, or if you don't really understand that, you can use this formula instead. Just ask yourself, would this number be like bigger or smaller? The Z S over root N. Would this number be made larger or smaller if I increased the value of n? You can even put in some dummy numbers and see what happens when you put the number 10 in there versus the number 100 versus the number 1000. If you put 10 in there, we get S over 10, which is some number. If you put S over 100 or S over 1,000 or S over 1,000,000, this number gets smaller and smaller and smaller, which is your margin of error, and our confidence interval gets smaller and smaller and smaller and smaller as well. You can always refer back to this if you get questions like this where they're saying what happens when the sample size increases, or you can have a little think about it. Celebrate. Alright, so here we have a nice little question. A random variable x is normally distributed with a mean of 36 and a standard deviation of 4. So we can see this as our population mean and our population standard deviation. So that's mu equals 36 and sigma equals 4. Now, the respective mean and standard deviation of the distribution of x bar from repeated random samples of size 9. So we're talking about sample means here, and I've got a nice little formula here. So the mean of the sample means, we use x bar for that, and it's just equal to mu. Could not be simpler. It's 36. So that brings our answer to C or D, and then the question is, how do we find our standard deviation of the sample means? S is equal to sigma 4 over the square root of the sample size, 9. So 4 over 3. I think I see my answer here. The answer is D. Done. Relatively straightforward. Use these formulas. You can't go wrong. So for this question, we'll do a tiny little mini lesson because there's 4 letters here and we really want to understand what they mean. So let's consider like population heights. That's what we're thinking about, heights of people. So let's go through these letters in turn. The distribution of X is always normally distributed. Now what is X? X is the individual heights of the people. So part A says the distribution of X is always normally distributed. Not always the case. Imagine if you were at a special convention for little people and basketballers, right? That is not going to be normally distributed. The distribution is going to look like that. Lots of shorter people and lots of taller people and not really many people in the middle. So, A, not always true. The population distribution is not always normally distributed. Now, capital X bar represents the sample means. And so the question is, if you take a bunch of samples, sample, will the distribution of those sample means be normally distributed? And it says here the distribution of X is always normally distributed. And you might think the answer is yes, but no. The thing that you should have learned in your maths class is that they are normally distributed if the sample size is large enough. But they don't talk about how big the sample size is. They're using this word always. So the distribution of the sample mean is not always distributed, only when the sample size is large enough. Jumping down to part D, the value of mu changes when different samples are selected. Now, mu is the population mean. And just because you choose 10 people, it does not mean that you've changed the average of the heights of all of those people. So, the population mean does not change depending on which samples you take. Which, of course, brings us to lowercase x bar, which is an individual sample mean. So you've taken a sample and that, whatever the mean of that sample is x bar. And then you take another sample and you get a different x bar because you've sampled different people, you sample different people and you sample different people. The value of x bar changes when different samples are selected. You bet it does. The answer is C, celebrate. Alright, so we have a nice little question here, a complex numbers proof, and we're going to have some fun with this one because when I look at the QCAA solution, it looks like this, and you can take a look at it and pause the video and understand they're working out, or they also had another method. This is method number 2. I'm not going to use either one of those methods, and the reason I'm not going to use either one of those methods is because they use complex numbers in component form. Basically, you let z equal a plus bi, and you move forward, and you're done. Again, rewind the video, you can look at method 1, you can look at method 2, but that's what they're doing. They're letting z equal a plus bi. I am not going to do that. I'm going to do something I think is more elegant, and instead I'm going to let z equal a cis theta. So I'm going to deal exclusively in polar form for my complex number. So let's write a left-hand side and a right-hand side of this equation because we're doing a direct proof. Left-hand side, right-hand side. Okay, now we've got the magnitude of z, so let me write it out. Magnitude of a cis theta, because I'm letting z equal a cis theta, over, and here's our first thing that might blow your mind, we've got a cis theta multiplied, and then the conjugate of a cis theta. Now, you've probably dealt with the conjugate in component form, but maybe you haven't spent a lot of time doing the conjugate in polar form. Look at what a cis theta looks like. It's a complex number with length a and an angle here of theta. And you should know, if you spend time drawing pictures, that the conjugate of a complex number is reflected over the x-axis. Which means that if this is z, then z hat, the conjugate of z, has the same magnitude, but a negative angle. So, a cis theta times a cis negative theta. Okay, done. And that's a property that we should know of conjugates in the same way that you know that a plus bi, a minus bi. are the conjugates of each other, we should know that a cis theta and a cis negative theta are the conjugates of one another. So that's my left-hand side, and my right-hand side is z to the the magnitude of z to the negative 1. So the magnitude of, and z to the negative 1 means 1 over a cis theta. Okay, done. I'm going to remove this picture now. We'll keep working down our left-hand side. So let's look at this. The top says, find the magnitude of a cis theta. It's staring straight at me. The magnitude of a cis theta is that thing right there. It's a, right? Because we drew it before. This is a, and the angle, that's theta. That's literally what it is. A, job done. Okay, now what's happening here? We've got a cis theta times a cis negative theta. I've got a formula for that. It's sitting on my formula sheet. If I want to find the product of two complex numbers in polar form, right, it's going to be R1, R2, so the magnitudes multiplied by each other, a times a, which is a squared, and then it's going to be cis theta 1 plus cis theta 2. So this plus this. Okay, so cis theta minus theta. Okay, very, very nice. Now, of course, what is theta minus theta? It's 0. So we've got cis 0 here. Now, that means, if we think about what this is, it's a complex number with length a squared, and the angle it's making is 0. It's purely real. It has a magnitude of a squared. So we end up with a beautiful a over a squared, okay, and 1 over a. That's definitely as far as I can go with the left-hand side. If only there was something now that I could do with the right-hand side. Let's move some things out of the way. Okay, and how am I going to deal with this right-hand side magnitude of 1 over a cis theta? Well, I'm going to use a little trick here, and I'm going to represent the number the number 1 as a complex number. All right, so let's think about a Cartesian plane. Here's the number 1. A complex number that's purely real, we can represent that as 1 cis 0. And then here we have a cis theta. Now, of course, we have a complex number now divided by a complex number, and we have a formula for how to do that. We're looking for the magnitude of 1 over a. So because we're doing 1 divided by a here. And then we have cis 0 minus theta. Okay, and then I'll just tidy that up. And then you might look at this and you think, well, yeah, but what am I going to do with 0 minus theta? How does that help me? Who cares? Because we've got a magnitude here, the magnitude of this polar form of a complex number. And of course, same as over here, when we're looking at the magnitude of a polar form complex number, it's staring us right in the face. Done. Okay, what do I see? I see a left-hand side equal to a right-hand side. And I reckon I've nailed that. Celebrate. All right, I think this is a fun little question. These sorts of questions have come up before, and I have solved them before using component form style stuff. But I do think that there's something to be said for having an understanding of complex numbers that allows you to use the polar form for these questions. I think it's an easier way to work. Let me know in the comments. Okay, so this is a fun little question here. It's a little bit hard to know how to start, but let's think about what's happening. An object of mass 2 kilograms is moving with a constant velocity of v equals 3I plus k. All right, so the object is moving, boop, 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 and it does have some weight to it, so that makes me think about force equals mass times acceleration. Okay, so it's moving, 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 moving. But suddenly, two forces, two people, let's say, come along and give it a shove. And one of them shoves it in one direction, like an arrow like this, and one of them puts some different force on it like this. And obviously when that happens, it's going to interrupt what it was doing, and now it's going to start doing something else. Okay, so that's kind of the idea of what's happening in this question. So why am I talking about this? Well, one, it's always a good idea to conceptualize your questions, but two, what I want you to understand is that this object had like what I would call an initial velocity, and then two forces acted upon it. And remember that force equals mass times acceleration. And so that means that that accelerated the object and it applied an acceleration to it, which then gave it a new velocity. Okay, so that's kind of the image that we're working with. So let's first of all deal with these two new forces that are acting on it, because initial velocity, we'll probably have to deal with that a little bit later on. Now, if two forces acted on it, force 1 and force 2, we can find the total force, or the net force, that acted upon it by just adding these two forces together. Nothing overly hard there, two forces, group-like terms, and we end up with a net force acting on this object of 4tj minus 2k. Now remember what I said, the object's moving, and then two forces act on it, and it accelerates it into a different direction. Now what is that acceleration? Well, I have a force and I have a mass, so I can find the acceleration, because force equals mass times acceleration. So force equals mass times acceleration. That means that force, which is 4tj minus 2k, is equal to the mass 2 times acceleration. And I can rearrange that a little bit, dividing both sides by 2. And I can say that acceleration is equal to divide by 2, 2tj, and divide by 2, negative k. So my object was moving, two forces act upon it, and the object was accelerated with this, 2tj minus k. Now that's the acceleration of the object, but the object's moving with some velocity, and then it shifts and it starts moving with some other different velocity. The question is, what velocity does this acceleration produce? So let's come up with a velocity function here. All right, so velocity is equal to the integral of 2tj minus k with respect to t, and then we integrate that, 2t squared over 2, so we end up with t squared j minus kt, put some little squiggles here, plus c. Okay, don't forget your plus c always. All right, now what do I have? Okay, I had an object that was moving with some initial velocity, and then it got acted on by two objects, and then now it's got a new velocity. Okay, initial velocity. I can use that initial velocity to find c, because we can treat the moment that this happens, right, at time 0. The moment when these two forces hit, like yes, it was doing stuff beforehand, but in terms of this question, this moment here when the two forces hit it, that's time 0. So at t equals 0, velocity equals 3i plus k. All right, so let's sub 0 into here and here, and we'll know what our c value is. But because these are polynomials, if I put 0 in here, I'll get 0j. If I put 0 in here, I'll get 0k. So actually, I can put that 3i plus k straight in here for c. Keep in mind, that's a dangerous move, so you do need to double check that actually when I do put t equals 0, yes, these are going to disappear, and yes, c is going to be 3i plus k. Don't think that just because that's the initial one, that you can put it straight in there. You can't. Only if these do disappear when you sub 0 into them. All right, so I now know my velocity. Let me write it down. Now I've just rewritten t squared j minus tk here, and then replaced c with my 3i plus k. Bear in mind, while the camera was off, I swapped my t and my k. It just didn't really look very nice to put t on the front there. Not technically wrong, but a bit weird. Okay, let's just put this in a better order. 3i. The only j here is t squared j. And then this, we have negative tk and we have plus 1k. So we can do a little bit of factorizing here and do like a 1 minus t k. That is a really nice velocity function. Now, what does that velocity function tell us? Remember, the object was moving and the object was moving. This is this, okay? This is our new velocity after that those forces were acted upon it. Okay. Now, you would have already seen it earlier because one of my transitions was off, but momentum equals, or P equals mv. So momentum equals mass times velocity. And it's asking us to determine the magnitude of the momentum of the object at t equals 1. Now, we can put t equals 1 directly into my velocity. And in fact, I think I will do that. So let's let t equal 1 and let's find the velocity at that time. Subbing 1 in here and 1 in here, that k, we get 0k. So we end up with just 3I and 1j. So that's the velocity at time equals 1. But what is the momentum at time equals 1? Well, that is equal to P equals mass, and we know it's a 2 kilogram object, times whatever the velocity is, 3I plus j. That's kind of it. I guess I will expand it, 6I plus 2j. Determine the magnitude of the momentum when t equals 1. Well, this is the momentum, not the magnitude of the momentum. Now, the momentum is just a vector. To find the magnitude of any vector, 6 squared plus 2 squared, we end up with the square root of 36 plus 4, 40. I think I can do a little bit better than that. That's like 4 times 10. I can bring a 2 out. I can get 2 root 10. The magnitude of the momentum, 2 root 10. And you might wonder, oh, hang on, momentum, what are the units for momentum? Look at the formula and it tells you what the units are. It's mass, so it's kilograms times velocity, meters per second. Momentum, 2 root 10 kilogram meters per second. Fun little question here, there, a little bit in it, and probably not immediately apparent what you should do with it, but once you get stuck into it, it's a fun one. Last one. So this is a real doozy of a question here. So while we're doing this question, I really want to give you a peek inside my head and see what happens when I read these complex, unfamiliar questions. The thing I want you to understand, first of all, is that maths teachers, even really good ones, and I'm not saying I'm one of those, but even really good maths teachers, when we read a question like this, we have no idea how to get from the beginning to the end. All we have is an instinct for like a first step. Okay, so what have we got? We've got a differential equation, so that's making me think, okay, I've got to work with differential equations. The current is this, time is this, voltage is this, blah, 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 and I've got some formula. Okay, now this in external exams comes in handy sometimes, where K, R, and V are positive constants. Okay, so these are all positive numbers, and T is greater than or equal to 0, so also basically a positive number can also equal 0. Okay, this is the bit where like this question is so out of left field. Assuming that there is no current in the electric circuit initially, all right, so initial something, show that the size of the current can never be greater than V over R. Okay, so what's current again? Current is the letter I. All right, so let me make a note to myself. I can never be greater than V over R. All right, so this is my note to myself. Never really deal with questions like this, but I feel like this is like an important little piece of information. I might just save that. So, with no idea of how to deal with a question where I've got to prove that something can never be greater than something else, what I do have is a differential equation, and maybe the only tool in my toolkit is to solve the differential equation. So maybe let's do that. All right, so some interesting stuff going on here. Okay, so I'm going to start solving my differential equation. So I'm just going to have K di dt equals V minus I. Now you've got to be mindful with this question that there are numbers here, right? K, V, and R are all numbers. We don't know what the numbers are. They change, they're variables, but they're numbers. Okay, now this feels like a separation of variables style scenario here. So I might just rearrange, make it di, and now I'm going to bring all this v minus ri to here, so dividing by v minus ri, so it's going to be k v minus ri, and we're going to integrate that, and then what are we left with over here? Well, we're just, because we divided both sides by v minus ri, we're just left with 1 here. and we're integrating with respect to t. So separation of variables, that's something we're looking at. Now, still no idea how to get to here, but so far all we're doing is solving a differential equation and crossing our fingers that we end up in the right spot. Now, this is an integral that you should be familiar with. We're going to end up in a natural log. We're going to have, if we brought the k out, we'd have 1 over v minus ri. And the integral of 1 over v minus ri is equal to 1 over negative r ln absolute value v minus ri. All right, so that's where we would end up if it was 1 over, but it's not 1 over, there's a k there as well, so we multiply it by k, and we're going to end up here, absolute value. All right, so there's our integral of the left-hand side, the integral of the right-hand side. The integral of 1 with respect to t is just t, and there is a plus c here somewhere because we've integrated both sides. Okay, so far so good. We're solving a differential equation. We've got a c. It feels like an obvious next step with no idea how we're going to deal with this yet would be to find c. And assuming that there is no current, current is I, in the electric circuit initially. So at t equals 0, I equals 0. Let's sub that information then in there and find c. Well, that actually comes out really nicely because what we have, if we look here, at t equals 0, so that's just 0. So my right-hand side just ends up being c. And on the left-hand side, negative k on r ln v minus ri. And that ri, that I is 0 at time 0. So that whole negative ri disappears and we're left with just ln absolute value v, negative k on r out front. So that is our c value, which means we can place all of this here and we've kind of solved our differential equation. Okay, so it's worth pausing here and thinking about what's going on. We have this thing here, right? And I, in terms of like functions, it's like a y or an x. And we've got t here in terms of functions, that's like a y or an x. But k, r, and v are all numbers, right? And so that means that negative k on r ln v, this is a number. It could just be like the number 5 or something like this. So we have a function equals t plus the number 5. All right, so how can we rearrange this? How can we make progress from here? Well, it feels like I've got this natural log, right, with something out the front here, right? So what if I was just to have the natural log? Because if I just had the natural log, I might be able to work in this not in terms of logarithms, but in terms of exponentials, right? That sort of opens up some freedoms here. I also see this like kr, this kr, I see it like repeated. So it feels like, okay, let's divide both sides by negative k on r. Let's do that. So doing that leads us here with a nice little ln absolute value v minus r, right? Now, when I divide t by negative k on r, I get negative r on k, right? Dividing by a fraction gives you the reciprocal. And then dividing this by negative k on r just gives me ln v. All right, so far so good. I have ln v, I have t, and then I have this number on the end. Now this really is the place that you're sort of starting to go, okay, I've done as much as I can. I'm heading towards this place. I'm still not presenting itself. What else can I do to this? Like, what else can I do to this that might reveal something? And we can write this in exponential form, right? So we could write it as v minus ri equals e to all of this, e to the negative rkt plus ln. And a little trick here, see v, we were told v's always like a positive constant, so we actually don't need our little absolute value here. We can just write ln v. So made myself a little more space here, and let's talk about what's going on here. We have e to the power of something plus something, and so this is where, like, I got no idea where I'm going, but e to the power of something plus something, I know that I could rewrite that as e to the power of something times e to the power of something. Okay, so that's index law stuff. And things just slowly reveal themselves as you go, right? Because I see e to the ln v, well, I know e to the ln is just whatever this is here. I've done that before in methods. So that just becomes v. So it's v times this. So now I have v e to the negative rkt equals v minus ri. Okay. And then, like, I'm seeing v's, I'm seeing other things, but I feel like I'm getting at least a little bit closer because I've got this idea. Right, so IV and R, I've got IV and R here, and now I'm starting to think about what's going on. Okay, what do I have? I have like a number, like the number 5 or whatever it happens to be, and then e to the power of something, like an exponential function. What does an exponential function like that look like? An exponential function like that looks like this, right? It's like a decay curve. Never dropping below 0. And so this is going to be a key here, because this is a greater than question, and now I know something. Now I know that this is always larger than 0. This is always larger than 0, which means that therefore v minus ri is always larger than 0, right? Because this is always larger than 0. So if v minus ri is always larger than 0, I want to get I by itself. So I could say that v is larger than ri, and v divided by r is larger than I. Now I used a very weird symbol here. I said that I is not greater than v over r. Another way to say that would be I is less than v over r. And this says I is less than v over r. We've proven it. Now, do you have to be able to make a small leap towards the end here? Yeah, I think so, but it's not a huge leap, and you're getting all the way to here just by solving differential equations, and then you're thinking, oh, how else could I look at this? And then you've got to see that little bit. But that's why we practice these questions, so we can see things in an exam in these complex, unfamiliar questions. I'm going to celebrate that. So that's another week done and dusted. That was week 24. Link in the description to week 25. We are closing in, but we still have some more work to do, still got some more questions to do. Catch you next week.